Everybody, and welcome back to the next part of energy and enzymes. I think this is part 4. So before we learned from vocabulary that the enzyme helped with a reaction. The substrate is like the reactant. The product is the product, it's the end result. And the active site is the part of the enzyme that does the job. And we also learned some properties of enzymes that they are not consumed in the reaction, but they can be affected by cell conditions. So we're going to continue this. And we're going to learn a little bit about naming conventions. Basically, it's pretty simple. Usually an enzyme ends in ASE, and it's named for the reaction that they catalyze. So for example, sucrase, ASE, that's the enzyme, it breaks down sucrose. Proteases are a group that break down proteins, and lipases break down lipids. DNA polymerase is a slightly different one because DNA polymerase is not a breaking enzyme, it's a building enzyme. The key there is polymer is right in the name, and we know that a polymer is something that is built. So DNA polymerase builds DNA, it makes it longer, and then pepsin, a little different because it ends in SIN, breaks down proteins. The name there comes from polypeptides. So that is how they are usually named. Now, in terms of how enzymes work, we used to use the lock and key model, and the lock and key model is a very simplistic model of how enzymes work. The lock and key model basically shows us that the substrate fits right into the enzyme's active site. And that is due to hydrogen bonds and maybe ionic bonds between the substrate and the enzyme, like a key fits into a lock. And we see that in the picture. Like we just see that the substrate fits right into the active site, just like you would put a key into a lock. It's very, very simple. It's specific, and there's that correct hydrogen bonding already present. So shape is what's important there. The induced fit model is more accurate. It doesn't mean the lock and key is wrong necessarily. This is just kind of added on top of that. The induced fit model still tells us that we have a 3D structure of an enzyme, and the substrate specifically fits that 3D structure. That has not changed. The substrate binding, though, is going to cause the enzyme to change shape, which is going to give us a tighter fit. Remember, that's called a conformational change. And it is going to bring chemical groups in the right position to catalyze the reaction. So a good picture of this here, notice that the active site has a particular shape. The substrate can still fit there, but once the substrate has fit, and once those hydrogen bonds and weak ionic bonds have done their thing, it causes a conformational change that leads to, notice how the shape has changed, it leads to a tighter fit. So that is the induced fit model. Okay.